Alright class, now today what we're going to do in this lecture, we're just going to do some practice problem for thermodynamics. This is our first practice problem. You can pause me, write this down and then do this. I'm going to ask you that calculate the delta H, delta S and delta G for this reaction. Okay, so let's do this together. So I'm going to ask you to calculate the delta H, and remember that when you do that, when the delta H of the formation is given, is pretty easy. It's product minus reactant. It's product minus reactant. And just a reminder that what does this mean? This degree sign, that means a standard condition, right? Standard condition, 25 degrees and 1 atm. Okay, so product minus reactant. So my product over here is I have methane and O2. The delta H of the formation for O2 is 0. And if you know, if I hadn't given this to you, you should know that, because delta H of the formation is basically how much energy is released or required when you make something from its pure element. And that's how O2 exists, right? That's how O2 exists. And let's see. That's how O2 exists. That's how it exists in nature. It's in pure elemental form, so it's going to be 0, the delta H of the formation. Okay, then I have a delta H of a reaction is product minus reactant. Now let's do this together. So my product is methane is 127, and remember the delta H of formation is kilojoules per moles, so I have to multiply by the coefficient in order for the moles to get cancelled out. So it will be 172 times 2 plus 0 minus, and then my reactant would be minus 239 times 2. So add up all the product together and then add up all the reactant together, product minus reactant. What I end up getting is 732 kilojoules. Again, it was delta H of the formation which I used, product minus reactant, and don't forget the coefficient. Don't forget the coefficient. It was kilojoules per mole, but when I multiply by the coefficient, the moles get cancelled out. What I end up with is just kilojoules. So far so good, because the moles get cancelled out. Don't forget to multiply by coefficient. Alright, so far so good. Then I give you the S values, the entropy values as well. And if I give you the entropy values the same way, you can do product minus reactant for also delta S. My product, it would be 186. Again, you have to multiply it by number of moles, right? Plus, now for O2, delta H of formation was 0, but not the entropy. Entropy is not 0. Again, the coefficient is just 1, right? So here is my product minus now my reactant. Again, don't forget to multiply by the coefficient, 127 times 2. So product minus reactant. You add up all the product and then you add up all the reactant and you subtract them. What you get is 323. Now, what's the unit? Remember over here, the unit for delta S was joules over Kelvin moles. The moles are cancelled out because I multiply them by the coefficient. So what the unit ends up being is joules over Kelvin. So far so good. Okay. Now, I ask you to calculate the delta G. I didn't give you all the delta G value to do product minus reactant. That's okay. That's one way to do it. If I give you all the delta G values, you can figure it out by doing product minus reactant, how we figure out delta H and delta S. But if I don't have that, another way to do this is by using the Gibbs free energy equation, delta H minus T delta S. Basically what this equation does, it looks at the relationship between delta H and delta S to figure out if a reaction is going to happen or a reaction is not going to happen. it looks at the balance between these two, the balance between delta H and delta S. Now, before we do that, I want to come back here and talk about this problem a little bit more. Now, if I look over here, this is my delta H. Is this favored or not favored? This is favored, right? This is favored. Why is it favored? Because if delta H is negative, is favored, delta H positive is not favored. So I just made a huge mistake. So this one right here is not favored. So delta H negative, exothermic, is favored. Delta H positive is not favored. So this one right here, this is not favored because we required energy, versus is a lot better to release energy than to require energy. So don't make the mistake that I just made. Delta H positive, endothermic, not favored. Delta H negative, exothermic, would be favored. So far so good. Okay. Now we come over here. How about this one right here? Remember about delta S. Delta S, if it's positive, is favored. If delta S is positive, is favored. If delta S is negative, is not favored. Because positive means disordered, and we said disordered is favored because it's easier to be messy. Okay? So this one is favored. And this one not favored. So we have one that is not favored and we have one that is favored. If they were both favored, the reaction will go. Both not favored, the reaction would not go. But we have one that is favored, one that is not favored. Then what do? We have to look at the delta G. We have to look at the delta G because delta G has delta H and delta S. So it looks at the balance between these two and it will determine which one is going to win. Alright, so the other thing you have to really care about is unit. Because right now, this is joules and this one is kilojoules. So you have to make sure they're both the same unit. It doesn't matter which one you want. You can pick kilojoules, you can pick joules. The only thing is they both have to be the same. I'm going to go with kilojoules so my numbers are a little bit smaller. So delta H is going to be 732 kilojoules. Minus, what is my T? My T is 298 because we said this is at a standard condition. Okay? That would be 298 Kelvin times, okay, I'm going to convert joules to kilojoules, so 0.323 kilojoules over Kelvin. And as you can see, the Kelvin would cancel out. What I end up with kilojoules. Okay. Now, if you actually do the math, what you end up is 636 kilojoules of energy. Now, what does that mean? What does this mean? Again, a little review. If delta G is negative, the reaction will go. If delta G is positive, the reaction will not go. So, what can you tell me? Will the reaction go or not go? Based on this, the reaction was not go. One was favored, one was not favored, but we had to put it all together to see what's the balance between these two, which one is going to win. And this ends up being a positive delta G, so the reaction is not favored. So far, so good. Okay, ready to go to part D? Here's part D. How much energy is required to decompose 50.0 grams of methanol? So how much energy is required? Now, every time they ask you how much energy, what that means is, what is the delta H? Because delta H is the energy and delta S is the entropy, right? All right, how would we do this? First of all, grams will get you nothing. The first thing you should do, you should convert grams to moles. That should always be the case for any chemistry exam you take. You don't know what to do, you see grams, convert it to moles, and then let's see if we can get somewhere. I get 1.56 moles of methanol. Okay? Now, there's two ways to do this. You can do it with using to cancel out, or I can do a cross multiplication, which I really like. I'm going to put up the reaction on this page right now. This was a reaction. Again, this is all part of the same problem. And the delta H that we calculated was 732 kilojoules. So what this is telling me, that for this reaction to happen, I need, because this is endothermic, I need 732 kilojoules of energy is required. Okay? Now, when this reaction go, I have to put in 732 kilojoules of energy. Now, when I do that, how many moles of methanol do I need? 2. For 2 moles of methanol, 732 kilojoules of energy is required. So, if I have 2 moles of methanol, 732 kilojoules of energy is required. Now, how many moles of methanol do I have? I have 1.56 moles. How much energy is required? So you can do a cross multiplication, which to me, that's kind of, I like cross multiplication. It makes sense. Let's do it together. So this problem says, for this reaction over here, the delta H is 732. Energy means delta H. Endothermic. I need this much energy for this reaction to go. Now this reaction requires 2 methanol. 2 methanol, that much energy. What if I have 1.56 methanol? Then how much energy do I require? So you just do a cross multiplication. All right, beautiful. So far so good. Ready to do our last problem? Let's do one more practice problem. Again, these are going to also help you in lab. Okay, read this for me. You have 2 solid chemicals that are mixed together. The beaker gets hot and the gaseous ammonia is smelled. Now, the sign for plus, minus, or 0 for each of the thermodynamics properties. Okay. Now, the beaker gets hot. If the beaker gets hot, are you an exothermic reaction or endothermic reaction? You are an exothermic reaction, right? If the beaker gets hot, you are an exothermic reaction. Why are you an exothermic reaction? Because, again, exothermic reaction, they release energy. When they release energy, the energy goes to the surrounding, so the beaker is going to get hot. So what is my delta H? My delta H is negative. Because again, the beaker gets hot, exothermic, release the energy to the surrounding. Now, what is the delta S? What are you forming? You're forming an ammonia gas. If the gas is formed, what does that mean? If you form gas, gas means what? That means you become more disordered. Gas means you become more disordered. So you're gonna add more disorder to the system. So the delta S is gonna be positive, because disorder means delta S is positive. Okay, and this was exo because beaker got hot. Now, how about delta G? Remember, in this problem, you mix things together and you smelled the ammonia. So you made something. So the reaction happened. So the delta G would be negative because the reaction goes. How do I know the reaction goes? Because I smelled gas. So something happened and the reaction went. Okay, this is a good practice problem for your lab. So think about it. I can give you think about delta H, plus or minus. Look at the surrounding. My surrounding gets hot, exothermic. My surrounding gets cold, endothermic. Delta S. Every time you form gas, usually that means you become more disordered. Delta S is positive. Now, if a reaction does happen, then the delta G is going to be negative. It happened here because I added things together and I smelled gas. So something happened. The reaction went. All right, nice job. We'll talk more about thermodynamic next time. There's one more part we need to go over, but hopefully these practice problems helped you understand what we've talked about so far before we go to the last part. I will talk to you guys next time.